Let's begin with the question, what is loxodrome? Sailors refer to it as the rum line, and use it as a breadcrumb trail to navigate their ships. In our context, loxodrome is a breadcrumb trail which navigates energy and matter. The energy being characterized by the frequency of construction, and the matter represented by dots, or breadcrumbs forming the path. In that sense, energy and matter represent analog and discrete components of our universe, which perhaps is reflective of dark energy and dark matter behavior. As such, loxodromes have interesting physics properties. For instance, the velocity relations for point P spinning around the sphere are as illustrated. For globotoroids, velocity relations at point P are identical. Some interesting observations about the frequency of construction. Generally, frequencies of construction for celestial objects are very small, suggesting that cosmic processes are slow. In contrast, the velocities at which these objects spin are very fast. Physics of spheres and globotoroids becomes even more interesting when the point P contains mass, and becomes a particle. In this case, the conservation law of angular momentum choreographs the particle spin around the geometries considered. Now we put the physics to work to simulate spinning of particles with conserved angular momentum. The dark space of energy and matter is animated as a silhouette, while mass particles are shown in color. As particles move, they leave behind a breadcrumb trail, which seeds the silhouette. In nature, examples of such seeding are given by different celestial objects, for instance comets, asteroids and meteors. Let's begin with one particle seeding a sphere. As momentum is conserved, a particle slows down at the equator, and picks up speed at the poles. At the pole, the particle spins very fast as r diminishes. Next, let's take a look at two particles seeding a sphere. Although conceptually interesting, this scenario is unrealistic as velocity at the pole increases to infinity. Now, we take a look at one particle seeding a globotoroid. Here singularities do not exist, making both r and v finite for all times. This is more realistic. Here we have two particles seeding a globotoroid. Conservation of momentum pushes two particles rapidly through the wormhole. Perhaps, worm momentum expresses the best what happens to mass moving around a globotoroid. Mass squeezes through wormhole, and expands over globe. Wormhole task is to compress matter. Now, let's simulate two particles seeding a universe. As particles make their journey, they are seeding different energy states. While sparsely seeding high-energy states, the two particles are making their way toward low-energy states. The purpose of seeding is to produce more mass. The hypothesis is that most seeds grow to produce individual, or clustered, mass particles, while the remaining seeds convert back to dark matter. As seeding reaches the core, low-energy states become densely seeded. Typically, high-energy states lose seeds, and the seeded core emerges. The core opening is tight, and all of the globotoroid matter, seeds included, pass through it. The matter motion through the core is not affected by the massless matter. The matter flows surrounding the limit cycle without obstructions. Even the seeds are not interfering with flow. The game changer are mass particles that grow from seeds. They may form large mass clusters plugging the core. In such cases a huge angular momentum is built, and clusters have uneven spin. They spin faster in the middle of the core than at the core edge. This plugged flow condition is hypothesized to be the black hole. The difference in velocities across the black hole turns the core into the hot grind, which attempts to liberate its opening. Because of its large angular momentum, black holes have huge gravitational force that pulls in more free mass particles. This re-energizes the mass cluster, and mass recycles. All black holes have the event horizon boundary. This boundary is defined by the radius at which the linear velocity equals the speed of light, and is given by the Schwarzschild relation. Inside this boundary, a huge gravitational force spins and densifies mass particles. There is one more requirement a black hole needs to have. The core has to be completely covered by mass, and the limit cycle must be encased. If this is not so, the core flow is disturbed, and the core will not establish required gravitational force. In other words, the core has not reached the critical black hole mass. This required condition typically occurs with supermassive dying stars. If a dying star is not supermassive, it is unlikely for the core to reach the required black hole mass. In this case a very dense star with a quick spin is formed. Such stars are known as the neutron stars, or pulsars. Its quick spin most likely is caused by the close proximity of wormhole, which rapidly compresses a dying matter, while at the same time radiates a strong electromagnetic beam. Based on the present hypotheses, one should not conclude that the core appears only in dying stars. Recall, the core results from the fill, which is not present in spheres as they have singularities at the poles. The globotoroids, however, have no singularities. Instead they form a wormhole that allows a loxydrome to fill its interior. The core, having the most dense structure, attracts mass, if present. As such, the core is the source of the beginning and the end of mass cycle. For black holes and neutron stars, the mass is at the end of this cycle and is very slowly converted back to the dark matter and seeds. Since these are massless, they can seep through the black hole body back into the space. Quasars, which are more complex galactic objects, also seed the space, but because of their complexity they are not part of the present discussion. As the universe is seeded, the seeds grow and cluster to form baby stars. These baby stars are nurtured and protected by a fertile dust ring, or disk, which surrounds the newborn. Baby stars contain an undeveloped core that needs to grow and mature before they become massive stars. As a result, baby stars have a weak gravity field, which allows dust rings to spin off new celestial objects. This is how planet, moons and asteroid belts can be formed. As the baby star matures, it establishes strong gravity field that traps everything in its domain, and is very likely to remain faithful to its constituents until death. In conclusion, our universe is very much alive.